And so Vikram, after getting his undergraduate degree from IIT in Mumbai, went to Caltech, where he did his PhD and graduated in 2009, and then was a postdoc at Columbia University for a few years before coming here.
Yep.
And he's been here since January of 2014,
yep.
and he's going to update us on what he's been doing.
Okay. Yeah, thanks, Doug. Thanks for that introduction. And yeah, good afternoon. It's really nice to be here in front of the department and tell you what my group and I have been doing for the last 2.5 years or so. Yeah, so the title of my talk today is Quantum Transport in Graphene Derivatives. So essentially, I'll be talking about some very interesting transport phenomena that we are trying to observe in these very interesting materials and that we are observing. So for example, these two traces here are data that my students have taken over the last few months. And so I'll talk about understanding these things in the next 45 minutes or so. Okay. Okay. So the title of my talk, of course, or the topic is graphene, and I should begin by talking about graphene, which has been called a wonder material. It's because I guess it's been used all over the place, like in transparent electrodes and semiconductors. It's been talked about being used in solar cells, gas barriers, and so on. And there's very good reasons why people are trying to come up with so many uses for this thing. It's because it's the thinnest material out there. It's only 1 atom thin, of course. It has record electron mobilities. It's a really good conductor of heat. It's the strongest material ever. It's almost transparent, and the list goes on. Of course, we are interested in the physics of graphene, and it may not be a very well-known fact, but pretty much, I would say the first measurement that ever happened on single-layer graphene was this one here, which was the quantum Hall effect in graphene. So this was pretty much, I think, about a year after graphene was discovered, that two groups of people, the original discoverers of graphene, Gaiman and Vasilov, and actually my postdoctoral advisor, Philip Kim, came up, and they basically found the quantum Hall effect in graphene, namely the quantization of the transverse Hall conductivity, which you can see here along the y-axis. And the quantization is in units. I don't know if you can read this well enough. It's in units of 4e squared over h. And that has to do with the fact that there are 4 types of fermions, or 4 degrees of freedom in graphene. And we'll talk about this in just a little bit. So anyway, so the point is that it has some very interesting fundamental physics, and following this, there were a lot of other interesting observations that were made in graphene, namely the fractional quantum Hall effect and the observation of Klein tunneling and so on. And in fact, when the Nobel Prize was awarded, it was these phenomena that were actually cited for the reason, and not all of those applications. Well, the applications did not exist when the prize was awarded, but my point is that the physics of graphene is very interesting, right? And so my group here at the University of Utah is trying to look at a few different problems that are connected to the physics of graphene. These are 4 different classes of materials in some sense. They're all either connected to graphene or inspired by graphene in some way or the other. And so let me just describe them briefly. So so we have carbon nanotubes, which you can think of as rolled up graphene. You have graphene, which we are actually trying to strain in some very interesting ways, and that gives us some very unique properties, we think. We have these different class of materials altogether called topological insulators, but they share some very interesting electrical properties with graphene, and I actually call them, in fact, the community calls them a quarter of graphene, if you like. And then finally, we have these completely new classes of materials that we are trying to develop here in my group together with 2 other groups, and we're calling them metal organic graphene analogues. Okay, so before we get started talking about the research that we're doing, all of this work actually requires a fair amount of instrumentation and learning and equipment building and so on. And so I wanted to quickly give you like a virtual tour of the labs. So this one here is our synthesis lab, which is actually, I believe, right below this auditorium. It's B10 of this building. So we have in our synthesis lab, a tabletop atomic force microscope, a really nice optical microscope, and these are labs my students and I have basically built from the ground up, and so I guess we're pretty proud of them. We have a fume hood and an exfoliation station, so that's actually nothing that special, but we have this nice oven where we can grow materials. We have this precision transfer setup where my students and postdoc are actually trying to assemble new materials, if you like, from the bottom up in a layer by layer, atomic layer by atomic layer manner. So a typical process starts by the students, I guess, trying to make the material that they want to study, and then they move on to the nanofab, where the kind of work we do typically involves, pretty much using everything that the nanofab has, including optical lithography, direct writing, the focused ion beam, the transmission electron microscope, and so on. And so the students then end up, training on these equipment, and at this point they've gotten pretty good at working with them. We also use a bunch of the physics facilities quite a bit with the electron beam lithography in INSCC and the micro Raman as well. Okay, so at this point we move on to our measurement lab, where I guess I would point out mainly to this. So we have 3 different cryostats here. The main guy is our superconducting magnet fridge, which is actually sitting in this pit. So when fully extended, this thing is actually about 14 feet tall. So it's quite a big system, and it actually took quite a while it was custom designed, and it took quite a while to get made and installed, but it was installed earlier this year, and it's actually working out really well for us. And I'll be talking about a lot of data that we have gotten from this, and a couple of other cryostats as well. And so we move on now to talking about the kind of science that we are doing in our lab. After having essentially built up the lab and learned and mastered all of the the synthesis and fabrication techniques and so on. Okay, so the first one that I'm going to talk about is going to be the rolled graphene, or carbon nanotubes. And let me actually start. Oh yeah, this is the work of my graduate student Neda. And so let me start by describing to you what are single electron transistors, because this is something that's going to become pretty important in understanding this work. Okay, so the idea is that if you have an object, let's say like this dot here, that's so tiny that and let's say it's surrounded by some metal close enough. If you have an object that is really small, it would take a large amount of energy to add even a single electron to it, and so your classical charging energy to charge a capacitor, which is half q squared over c, even for one electron, becomes appreciably large, right? So we're talking about a system that tiny. So essentially, what happens is that because it takes a large amount of energy to add even one electron to this, the current is blockaded, and you really have no current that would run through the system, right? So So what one does is, one has this gate underneath here, and one can try and basically change its voltage and add charges, if you will. And the way to understand this is the following. So you have the total energy of a system of n electrons, which you can think of as as an interaction energy plus a potential energy in some sort of an external electric field. And you can recast this in the form of this quadratic equation in terms of CG/Vg, which is in some sense a measure of charge. Okay. So as I change my Vg, right, essentially what this is telling me is that I'm getting a series of parabola that are getting shifted, by one charge because of the fact that charge is discrete, right? So the way the system evolves is that it basically follows, the minimum of energy, and there are going to be times when these two parabolas are going to intersect, right? And basically what that means is that it's equally likely for the system to have n or n plus 1 electrons, right? And then your blockade that I talked about here is removed. And what one gets is one gets peaks in current then as you sweep your gate voltage. Okay? So that's the phenomenon that we are trying to explore. All right. So the systems are carbon nanotubes. So these are basically grown based on a technique that I developed when I was a PhD student, except that back then I was interested in studying really, I guess, short nanotubes, which were about a couple of hundred nanometers in length. And now we're trying to do this, we're trying to go to like an order of magnitude longer. And I'll tell you why that is in just a little bit. Okay, so here's some data that we've gotten in the last couple of months on devices like this. So I'm plotting the conductance as a function of gate voltage. And if I take this middle graph here, for example, what I have here is actually my valence band edge. So namely, this is my first hole. And I can start counting, and I could probably count to about 70 or 80 holes in this case. And this is my band gap, and then out here on this side, we would have the electrons, right? So what's nice about this is that this is a really nice system for basically getting, any number of electrons or holes starting from 1 up to, you could just go on and get up to like hundreds of electrons isolated on this carbon nanotube, and then you can actually start doing some very interesting experiments with them. So a couple of very nice things about this data are, is that, it's, as you can tell, it's really, really nice and clean. And, you can look at these clumps of 4, right? There's like very, very regular patterns of 4. And that has to do with the fact that, as I mentioned earlier, right, graphene or carbon nanotubes have 4 degeneracies, right? 4 types of fermions. Okay, so a few things about this. This is really, really special because the typical data trace looks like this. This is from another lab's paper that I picked out. The Marcus lab is actually a pretty well-known lab in this area, and you can see that our data is quite superior. So it's very nice data, and these are pretty much the longest, I want to say definitely in terms of the aspect ratio, the longest single electron transistors that anyone's made to date. And the nice thing about these is that they're very one-dimensional, and we want to use them to study 1D physics, right? Okay, so you might say, why 1D physics? Wouldn't that be pretty boring? And this is actually a graph I used, or a picture I used from a few years back, where most things are not really interesting in 1D, right? You don't want to be watching a movie in 1D, but in condensed matter, 1D is special. Okay, so good reasons for that. In higher dimensions, you basically have screening, and that screening is basically what gives you your quasi-particles and your Fermi liquid. In 1D, there is no screening. So essentially, what happens in 1D is that your quasi-particle has an infinitesimally small lifetime, right? Your quasi-particle just does not exist. And because your quasi-particle does not exist, you don't have a Fermi liquid anymore. Your low energy excitations are actually bosonic in nature. They're decoupled charge and spin waves, if you like. This is actually called a Luttinger liquid, which is a specific thing only to one dimension, as opposed to the Fermi liquid that you see in pretty much any other dimension, right? And what I'm really excited about is the fact that there aren't that many systems to study this really special 1D ground state, and I think we have one of them. Okay, so other interesting things, there is a crossover that happens to a more from a more liquid-like to a solid-like behavior at low density, which is what is called a Wigner crystal. So what we're trying to do here with all of our Coulomb blockade measurements is that we're trying to use compressibility to differentiate the solid from the liquid. Okay. So again, I want to remind you that in our Coulomb blockade, whenever the energy of an nth electron state became equal to the energy of an n+1 electron state, we got a peak, right? So if you look at the spacing between peaks, for example, what you would get is En+1 minus 2En plus En-1, which is nothing but the discrete second derivative, right? So that second derivative, d square E dn square, is nothing but the electronic compressibility. And so that's something that we have direct access to, right? And the fact that we have really long systems essentially means that this discrete derivative is actually becoming more and more accurate. And so that's something that we are actually trying to analyze as we take data to figure out whether we can actually demonstrate some sort of a liquid to solid crossover in these systems. Okay. So this was actually carbon nanotubes was the topic of my PhD, and towards the end of my PhD, I had actually written a review article in Nature just describing the different open questions in this field. And now that we have our lab and we have some really nice looking devices, I'm actually really excited to try out these experiments. A couple of other experiments I'm just listing here. There's what's called the spin incoherent Luttinger liquid, which is a slightly different ground state compared to the Luttinger liquid. Another thing that you can do with these really long and really clean devices is that you can superpose a periodic potential on them, and essentially you can make your own band structure, if you like, right? I mean, that's how you get band structure, by putting a periodic potential on, on pretty much, I would say, on a clean system of electrons. So we can play some very nice tricks and make some really nice experiments in this way. Okay, so I'm going to move on now to the second topic, which is strain graphene. And this is the work of my students Rachel and Enoch, together with my postdoc Ryuichi, and undergrads Greg and Ben have contributed from time to time. Okay, so what happens in these systems? So the idea is that we want to make use of the fact that graphene is more than just an electronic material. It's also, like I said, it's a really thin membrane. It's the smallest, it's the thinnest thing ever. It's really flexible. It's really, really strong. And so what we want to do is we want to try and warp it in different ways, in interesting ways, right? And see what happens, or what sort of effects do the electrons that are sitting on this lattice feel from all of this funky business. Okay, so okay, let me just put it very simply to begin with. Let's say we had our unstretched graphene, and then we had a segment of stretched graphene in just one direction, right? Okay, so an electron that comes in from here, right, would want to keep the same momentum going into this segment of stretched graphene, but the Brillouin zone no longer looks the same, right? Because the graphene has stretched, the Brillouin zone looks different, but momentum wants to be conserved, right? So in this space now, it looks like the momentum has actually, basically the electron has actually gotten a kick, yeah? So the momentum is actually pointing in a different direction in this space, right? So a direct consequence of the Dirac dispersion of this material means that a stretch like this enters the Hamiltonian like a magnetic vector potential. Even though there is no magnetic field in the system, you're getting the effect of a magnetic field. Well, a magnetic potential to begin with, right? So, yeah.
Does that, if it gets, like in your example, that it would be in a superposition of one kick up or one kick down, is that?
Yeah, that's a good point that you're bringing up. So it turns out that, so you can see these two different valleys. They're going in two different ways. So I think maybe you're trying to say that like time reversal symmetry would not violate.
When you measure it, you get one kick or the other. But
so I want to say that, basically the effect is different on the electron, whether it belongs to this valley or this valley. Okay, so an electron in one valley feels a kick one way, and the electron in the other valley feels the kick the other way. Okay, so yeah.
What exactly do you mean by the term Dirac dispersion?
Basically, the energy versus momentum relation, the band structure is linear. So it's E equals h bar k. It's just like this as opposed to a typical semiconductor, which would be parabolic. So it's just, it's the jargon, it's the term that's used in this field, right? The fact that you have this linear dispersion actually turns out to mimic, I guess, a lot of interesting effects that were first seen in, or first predicted in high energy physics, like Klein tunneling and Dirac fermions and so on. So, yeah. Okay, so carrying on, right? So the point is that a uniform stretch feels like a vector potential, and if that stretch were actually, say, made to change in space, then the curl of that vector potential would be non-zero, right? And so you would actually get a field, right? And so since neither of these are magnetic, we actually call them a pseudomagnetic vector potential and a pseudomagnetic field, right? And so you might think, for example, in real space, that not only is your electron getting a kick, but it's actually now, going around, and possibly for large enough strains, doing a whole cyclotron orbit. And so everything that a magnetic field would do, except that there is no magnetic field in this case, right?
apply to the spins of the electron too?
This would be an orbital thing, yeah. So, so the theory is actually really nice, and and indeed, back in 2010, this group in Berkeley, when they were studying these really tiny graphene blisters using an STM, in their DIDVs, they actually found peaks that were, separated as if there were actually Landau levels, and those Landau levels were coming from magnetic fields as high as 300 Tesla, right? Which is pretty crazy because that's probably like 4 or 5 times, well, definitely 3 times the highest field that can ever be made by man. The best field that one can have in a reasonable lab is 10 Tesla, right? So this is like totally out there. So, and other groups have actually reproduced these experiments on an STM, but there is really, I guess, a lack of other types of experiments to test this phenomenon, and there's actually good reasons for it. It's because it's really hard to strain graphene controllably, but we think we have actually the right skill set and tools to do this, and so we're doing this in my lab in 2 different ways. So one is we're basically building devices on flexible substrates like this polyamide here. So really thin, flimsy substrate, and then we try and stretch the substrate and then see how it stretches the graphene. The second way is we basically make these tiny inflatable graphene balloons, or bubbles, if you will, and that also ends up, we hope, changing the strain in ways we want to change. Okay, so both of these, as you can imagine, have had some pretty big technical challenges that we've had to overcome and that we have overcome in the last year or so. So the first one, right, I just want to point out that what we're trying to do is we're trying to to controllably change the sample that's actually sitting at, I don't know, like a Kelvin or so, inside the bore of a superconducting magnet, which is about 10 feet below where we are, right? And so we've basically designed and built this 10-foot-long driving rod that we can actually control from the top. That's actually changing, the strain profile inside of this superconducting magnet. And so that's been one of our I guess our triumphs. And then so this is that thing looking into the device. Building devices on flexible substrates itself is non-trivial because they're flimsy. They're you cannot actually do electron beam lithography on them. But again, my student and postdoc have overcome this challenge really well. And these are this is actually a device that they've made, which is a so I don't know if you can read this. This is actually a stack, a 5-layer stack that's built on this flexible substrate of graphite and boron nitride and graphene and boron nitride. So the idea is that not only do you want to have this this thing sitting on some flexible substrate, you also want to have it be of really high quality, and so you encapsulate this in this boron nitride substrate, which is a really good substrate for graphene. Yeah. Oh, it's just I will talk about it in just a little bit. So what we're trying to do is we're trying to compare a real field versus this artificial field, right? So it turns out that they have very different effects in terms of what sort of quantum Hall effects they give rise to, what sort of symmetries they break, and so on. Yeah.
So what do you specifically mean by strain? Like I've heard the terms like stress versus strain. Is that just like
stress is force per unit area. Strain is delta L over L. Right? Yeah. Yeah. Sorry. So that's actually a really good point. Yeah, as I was pointing out earlier, a uniform strain gives rise to a vector potential. A spatially varying strain gives rise to a field, right? Just because the curl of that will then be non-zero, and then you can actually get a field from it. So yeah. So it has to change in a certain way, and there's actually some theories out there that tell you what sort of structures you need to be making and so on. So it turns out that triangles actually are a good thing to make. Okay, so this is something that we've actually had a good amount of success in overcoming all of the technical issues, and so we are quite excited to try to start measuring these devices. In this one here with these bubbles, again, there have been different issues, I guess, which we have also overcome in the last year or so. So mainly it's been making small features and then trying to suspend graphene over these trenches or holes, if you like. But I guess I would say that the issues involved here have been definitely a lot more than in this project. Okay, so what are the things that we are trying to study? A few points that I want to mention. One is that the pseudomagnetic field, which I call small b, to be contrasted with a real magnetic field, which I will call capital B, right? It does not break time reversal symmetry, yeah, because it actually points in opposite directions at the two valleys, as I was mentioning earlier. So the effects of one field are going to be different from the effects of a real magnetic field. Okay, and the other thing that I just want to point out is that your graphene quantum Hall, which has a plateau of 4e squared over h, which has 4 types of fermions, right? Those degeneracies can also spontaneously break at high magnetic fields due to electron-electron interactions, and therefore you would get 4 plateaus of e squared over h instead of 1 plateau of 4e squared over h, just as a by the by. So that yeah. So what we're trying to do, or what we want to see, is the Landau levels of a pseudomagnetic field should actually give you a different type of a quantum Hall effect, than the Landau levels of a real magnetic field. because again, they're pointing in opposite directions in the two valleys. And so there's theory that says that you basically should have Landau levels that interpenetrate each other, and you should have a very odd-looking sequence of steps that would be jumping from one value to another, and so that would be something to look out for. Another one, like I said, is that you could, say, park yourself on a 4e squared over h plateau of a real field, and then try to tip the scales in favor of one broken symmetry or another by using this pseudomagnetic field. So that's another thing that we want to try. So there's another experiment that's actually ongoing off and on with Vali Vardeni's group, where we're trying to do Sagnac imaging of our bubbles, because there are theories that point to time reversal symmetry breaking in these bubbles, and so that's something that we want to be looking out for with Sagnac. So that's another project that's ongoing. And finally, our collaborator in materials has a prediction that strain graphene at high charge densities should superconduct, and I think these are all parameters that are within our reach. And so again, a bunch of experiments that we're quite excited to be doing at this point. So just as an aside, another thing that I have going on is microwave experiments, for which my student Rohit and Greg are actually building a sample holder for. And so this is something that they've built. So this is a sample holder about this big, I want to say. It's a microwave sample holder. This is this thing attached to the helium-3 insert that we have. And yeah, so Rohit is now trying to make devices for this particular experiment. Okay, so let me move on to the third part of my talk, which is what I call a quarter graphene. So this is the work of Sukong and so graduate student Sukong and high school student Jared Harmer. So the idea here is the following. Okay, so topological insulators are, well, they're not really connected to graphene. They're its own thing altogether. They are essentially 3D insulators that have basically that are insulating in the bulk and that are conducting on the surfaces. They actually have Dirac cones, just like graphene, on the surfaces, right? And so that's one connection. And so the idea is that it's basically one way to think about these things is that in the bulk of the material you have the band gap being inverted, and inverted compared to vacuum. And so when you go from inside of the material to outside, this gap has to close and open again, because going from inverted to the other ways. And so that's where you have concepts of topology that come up and so on, right? And so when it does that, right, it needs to close, and that closing happens on the surface, and that's why you have surfaces being conducting, whereas bulk is insulating, right? And so that's what's called a topological insulator, right? So it's probably a whole talk by its own, but yeah. So just to give you a quick history, the most common materials here are these bismuth, antimony, selenites, and tellurides. So a few things about topological insulators. They have only one fermion per surface, and therefore my point about being a quarter of graphene, right? And okay, so they were discovered in 2007, but as compared to graphene, for example, where pretty much the first paper that was published was the quantum Hall effect, it took about 8 years, for people to, basically be struggling with this material, because it basically has materials issues in terms of bulk conduction. So even though it's called an insulator, it's really not an insulator. I mean, the whole thing just conducts, right? And so in about 2015, the first group, actually this was Yang Chen's group in Purdue, they came up with a good material that would not conduct in the bulk and only conduct on the surface. And then at 31 Tesla, they basically found the quantum Hall effect in this material. And as of a couple of weeks back, there were 2 groups in the world that had basically seen the quantum Hall effect in these materials, despite there being a ton of them all over the world just trying to study it. Okay, so again, I want to point out that the quantum Hall effect here is should be in terms of E squared over h and not 4E squared over h, because there's just 1 fermion instead of the 4 species. Okay. So around this time, I actually got some MRSEC support in a seed grant together with my collaborator Taylor Sparks in materials to try and implement a program here on topological insulators. So here's some of our data on I would say our better looking samples that we've done a bit of back and forth with Taylor's group, where they make materials and then we measure them, and we make devices and measure them and so on. So this is what a device looks like. Out here, I am plotting the resistance as a function of gate voltage and temperature, right? So let's see. So starting from here, as I lower the temperature, I can see that the resistance is basically increasing, right? Going from blue to red, let's say. And we take this as an indication that the bulk is essentially, becoming basically becoming more resistive, and essentially the bulk is freezing out, if you will, right? And then at around 100 Kelvin, you actually start to see the trend reverse, where basically, the resistance starts reducing again as you go towards our base temperature, which in this case was, I think, 1.5 Kelvin or something. And that we take as evidence that, okay, we are now measuring our surfaces, and those surfaces are actually, the scattering, the probably electron phonon scattering is reducing because the temperature reduces, so the phonons get basically frozen out. And so at low temperature now, you have low resistance again. And so this is actually data from another device. And so you can actually look at the contrast between the room temperature measurement and the low temperature measurement, right? So the room temperature wasn't doing very much. The low temperature, so this is resistance as a function of gate voltage. It actually looks like what graphene should look like, right? Yeah. So the gate is changing the charge density. Yeah. So you're inducing more charges or taking them away. So for example, this is what we believe is the Dirac point, basically where our bands cross, right? And so on one side, so basically this would be hole transport. So you're basically inducing holes, and on this side, you're inducing electrons. Well, if you had just a single atomically thin material like graphene, the charges would be on graphene, right? So that's actually a really good point. We believe that, okay, so actually it depends on the thickness of the material. So we've been playing around with this a little bit. But I want to say safely for materials that are about 100 nanometers or thicker, the top surface is unaffected, and it is only the bottom surface that is actually being gated. Yeah, the gate is underneath. Yep, sorry. Yep. Okay. So, and actually, it turns out there's very nice evidence that tells you exactly that, which I will come to in just a bit. So, right. So, so at low temperature, I have this trace that looks pretty much like what graphene should look like. And so I will now move on to the Hall measurement, just to quickly recap what a Hall measurement is. Essentially, let's say this were my two-dimensional system, like a piece of metal, if you like. I pass a current from one end to the other. I hook up other ends to a multimeter. So essentially, I want to measure my longitudinal resistance Rxx and my transverse resistance Rxy as a function of other parameters that I have in my measurement, like magnetic field and gate and so on. Okay. So in a typical measurement, R versus, or Rxy versus B should be a straight line. And that's your Hall measurement, right? So what happens when you actually make your two-dimensional system really thin and increase your magnetic field to a really large value and decrease your temperature to the kinds of temperatures that we have in our lab? Essentially, instead of getting a straight line, you find that that resistance is actually quantized, right? And you essentially get plateaus that are, well, in conductance, there would be plateaus in units of E squared over H, right? And that is the celebrated integer quantum Hall effect, and then there are fractional versions of that and so on, which have actually gotten 2 Nobel Prizes. So again, to remind you, the quantum Hall effect in graphene happens in steps of 4 E squared over H, corresponding to the 4 species of fermions in that system. Okay, so let's see what happens in our topological insulators, right? So I'm measuring Rxy as a function of gate voltage and magnetic field, so as to have complete control of all of the parameters in our measurement. So let me take traces. Let me take a trace of this at 9 Tesla, which is in red, and I also have my Rxx, which is my longitudinal resistance, in black, right? And you can see that the red curve, which is the Rxx, is basically pretty antisymmetric in the gate, and it wants to try to flatten out towards the ends, perhaps, right? But there is an interesting difference between this point here and this point here, even though this red curve is exactly antisymmetric. And the difference is that the Rxx on this guy is actually going to 0, okay, which is what should happen in a regular quantum Hall effect. So the quantum Hall state is basically dissipationless. It has 0 resistance. So the Rxx goes to 0, which is what is happening here. But the Rxx on this guy, which is looks exactly like this one, is not going to 0. It in fact seems to be going to infinity, which is kind of interesting. It's telling us that this guy is dissipationless, whereas this one is quite dissipative, right? So let's do the tensorial inversion and actually plot the conductivities instead of the resistivities, right? And now again, my sigma xx is plotted in black as a function of my gate, and my sigma xy is plotted in red as a function of my gate, and you can actually see these plateaus form here in units of 1 E squared over H. So essentially we have seen, this was from 2 weeks back, we are, I would say, the 3rd group now in the world to see the quantum Hall effect in these materials. So we have seen the nu equal to 0 plateau, which is this one, and the nu equal to 1 plateau, which is this one. And something that I'm really happy about, we have seen it at a much lower field than those other groups. So while those groups would take their samples and go to the National High Magnetic Field Lab in Tallahassee, we can actually do our experiments right here. So we're pretty happy about this, and so we're trying to do follow-up experiments. And so the first one that we actually want to be doing is to be looking at the nu equal to 0 quantum Hall state, which is this guy, well, this one here. So this is nu equal to 0, and this is nu equal to 1. And the reason is that, like I said, it's dissipative. It's actually very different from your regular quantum Hall states. And theorists have already, come up with some ideas of trying to probe what is going on in this nu equal to 0 state more carefully. It turns out in this particular system, it has to do with, the physical edges of the sample, right? So not the edges of the quantum Hall effect, but the edges of the sample itself, which is actually, doing some, basically carrying some spin currents, as these guys are suggesting. Okay, so another actually bigger reason is that, is the whole point that that these materials have, one species of fermions as opposed to 4, and there's actually a lot of applications, if you like, where you would just like the one type of fermion, and one of the more exotic ones is this, I guess, search for Majorana fermions in condensed matter, where Fu and Kane, for example, came up with this proposal where they said that you could make normal superconductor junctions with a really clean surface of a topological insulator. And other people have tried it, but they haven't actually had, I guess, the kind of material and results that we've had. So we're definitely looking forward to trying something like this. So that's another example. Okay. All right. And so moving on to the last part of my talk. Is this essentially an area that we have started out here together with my collaborators, Feng Liu and Janice Louis in materials and chemistry, called metal organic graphene analogues. So the work I'm talking about is going to be the work of my student Neda and postdoc Ryuichi. Okay. All right. So the motivation for this part of the talk is the following. Again, it's related to graphene, and so the idea is the following. When Kane and Mealy, who one could call as the discoverers or the inventors of the field of topological insulators, when they made their proposal for this particular state of matter, they actually had graphene in mind, and they said that graphene could be a topological insulator if you are able to cool it down to a temperature of like a microkelvin, right? Obviously that is not possible. You cannot take a macroscopic thing and make its temperature to a microkelvin. An alternative way to the same thing is to try to make structures or materials that have the structure of graphene, so essentially that have a hexagonal or possibly a Kagome lattice, but have heavier metals corresponding to larger spin orbit coupling that could be linked through organic ligands. And so this is what are called two-dimensional metal organic frameworks, which is actually an area that is coming up in the last year or two. And what we are trying to do here is we are trying to make metal organic frameworks that have the structure of graphene, right, as opposed to any other structure. Okay, so the structures and the band structures are calculated by my collaborator in materials, Feng Liu, and so he has, for example, all of these very interesting structures proposed that are supposed to be, for example, a topological insulator and a churn insulator and so on. And the materials, basically the synthesis is done by Janice Louis in chemistry. And she is basically, between us, we're making two different families of compounds right now. So there's what we call MHAB, or hexaminobenzene, and then MBHT, or benzene hexathiol, where M is any one of these different metals at this point. Okay. So again, the point of this field is that we are trying to make materials that haven't been made before. So there's a lot of emphasis on the characterization and just trying to find out what exactly these things are. And so that's what we've been spending a bulk of the time right now. So here's some AFM and so basically atomic force microscope and scanning electron microscope images that Neda has taken, for example. So it looks like they're pretty flat and thin. So they're sub 10 nanometers thin. So they're pretty two-dimensional, if you like. They're pretty flat out here. So depending on the material and depending on the synthesis, we are able to get materials that are extremely two-dimensional, extremely thin, like graphene. And so here's actually a selective area electron diffraction image, and that I don't know if you can see these points on the 6 corners of an hexagon, right? So this is also telling you that the structure of these materials is bang on. So yeah, so it looks like we are actually making and trying to study the materials that we had in mind. Okay, so that's good. We are trying to look at their electrical properties through a bunch of different techniques, including optical lithography and shadow mask lithography and electron beam lithography and so on, because again, these are materials that haven't been made before or characterized, so it's really not clear to us a priori what is the right way of approaching them. But here's some results on a material that has given us our best result, which is copper BHT. Okay, so I'm plotting here the resistance as a function of temperature. You can see that the resistance decreases as the temperature decreases. So that's actually evidence, or rather, it's indicative of metallic behavior, which is interesting because there's actually a few firsts that we have gotten out of this material. Well, first of all, the conductivity of this material is pretty high. It's about 1,000 Siemens per centimeter, which, I mean, it may not compare with copper, but when you consider, organic metals, I would say it's actually it's pretty respectable. So it looks like it's a highly conductive organic material. It's the resistance decreases as temperature decreases, which means that it's metallic. And it's interesting to point out that there's actually not that many organic metals out there, and I've listed a few of them. So it looks like we actually have a highly conductive organic metal that actually shows a linear R versus T dependence, at least up to a certain point, which is suggestive of electron acoustic phonon scattering, right? Because so that's actually the kind of behavior that acoustic phonons give. But more interestingly, it's telling you that the optical phonons are actually out there at really, really high temperatures, because again, it's a testament to the strong carbon-carbon bonds that the optical phonons have a really high energy. Because if this were, I don't know, if this were bismuth something or the other, these guys would be totally taking off. I mean, you would actually have the resistance climb at least like a square of the temperature. It would definitely not be linear. So yeah, so there's actually, so we're trying to understand a little more about the scattering, or in general the transport in these, just by making more devices and trying to get some statistics. Yeah, in the next, I want to say in the next few months, one of the things that we want to do is we want to complete electrical characterization of this other material, NiBHT, which is actually the one that is supposed to be interesting. It's supposed to have this topological insulator ground state. The one that I just talked about, the CuHAb, the one that was really metallic, is actually not a topological insulator. But it turns out, so Feng tells us, that it should become superconducting at low temperatures, and there actually hasn't been a MOF, a metal organic framework out there that has superconducted, and so that's also something that we're hoping to look out for. And then, in the long run, we actually have a whole list of compounds that we want to make and test towards trying to get these exotic ground states. Okay, so to conclude my talk, I talked about, after describing the setup of the lab and the different processes that we use, I talked about 4 different areas of research that my group and I have been working on and have made different amounts of progress over the last year or so. So in the area of carbon nanotubes, we have realized some very nice looking data, pretty much the longest single electron transistors to date, and we are looking forward to studying some pretty interesting 1D physics with this. In the area of strain graphene, this actually has involved a fair amount of equipment building and technical know-how and process learning, but we have actually successfully navigated all of those steps, and we are looking forward now to studying pseudomagnetic fields in these materials. In the third topic of topological insulators, we have observed the quantum Hall effect on the surface of these materials, and we are, like I said, now the third group to be doing so, and we have actually seen this at a much lower field than those guys, which allows us access to a lot of experiments that we can do right here, and like I said, the ones that particularly involve a single species of fermions as opposed to 4, like in graphene. And finally, with our metal organic frameworks, these are completely new materials, and after a lot of characterization, we have basically found temperature dependence, actually the first metallic temperature dependence in a MOF, and we are continuing to study a bunch of other MOFs as we go along. Okay, so I want to acknowledge my postdoc Ryuichi, my graduate students, undergrads, the high school student in my lab, and collaborators whose work was involved in this talk. And yeah, I want to thank you, and I will leave you with my conclusion slide. Thanks. John.
I would think you have enough data on the upper left there to take your second derivative and get.
Totally, I agree. Yeah, and yeah, we're on top of it. Sorry.
What do you need more? You've got the compressibility, right?
Yeah, we got that data last week, and then I had to make this talk.
Okay.
Yeah.
What's the significance of having a material with one fermion?
Yeah, so it's a good question. I mean, it's there's a bunch of, well, so for spintronics, for example, you would like to have just the one type of spin. So that would be, one example, right? A lot of theorists have come up with ideas. For example, Majorana fermions, is this I guess is the latest or one of the entrants of high energy physics into condensed matter, and people have theorized that, okay, to make a Majorana fermion, you need the one type of a species that is superconducting, right? So that's another reason why you only want the one species. There's actually a few others as well, but yeah, so hopefully that answers the question. Yangshi.
Yeah. So, with the wind force and graphene experiment, you mentioned that you were able to hold that at a much lower B.
Oh, in this one, in the topological insulator.
Right.
Yeah.
So
In this guy right here.
what's the reason why you can get the
So I think it's.
whole effect at much lower B? Your sample is much more cleaner?
There's probably a variety of effects, a variety of reasons. So, okay, so, first of all, it is not an issue of Landau level spacing because, I would say even at 1 Tesla, the Landau level spacing is larger than temperature. So you should be, in the cleanest sample limit. And that does happen in graphene, for example. In the cleanest graphene, you can actually see the quantum Hall effect at 0.1 Tesla, right? So it's clearly not an issue of Landau level spacing versus temperature. It is an issue of sample cleanliness, right? So why our samples are cleaner than other groups? Well, we've been doing a lot of back and forth. We started out with pretty bad looking samples, and I would say definitely I want to thank my student and the growers for persevering and going back and forth until we were able to get this. But yeah, we've also been exploring on our own just cleaner device making. This is something that I have a lot of experience in, just really clean lithography that other groups are not doing. cleaner substrates. And I think this is, I'm hoping that this is only the beginning, and we can actually see much cleaner data than this one, because we have a few ideas that we want to try and implement. So.
Yeah, were you able to actually observe more steps and more plateaus?
No, so this is, well, so those guys were at 31 Tesla, and I think they saw something like 3 steps or so, 3 or 4 steps. We are at 9 Tesla. We have seen 2 steps. So if we take our sample to the high mag lab, I'm sure we will see more. We are trying to approach this problem by essentially trying to improve the sample quality in-house and do the same. But yeah, there's actually it's a really fascinating area, because so you actually now have 2 surfaces. So you have a top surface, which is like a quarter graphene, and then you have a bottom surface, which is like a quarter graphene. And what we're doing is that we are changing the charge density on the bottom. The top one stays exactly the way it is, right? And so it turns out that these systems are half-integer quantum Hall systems, okay? So the reason why you actually see the step at 1 integer is that you actually have a contribution from both faces of a Berry phase. So there's basically a factor of half that comes from top, and then there is a factor of half that comes from the bottom, but then the bottom is actually changing in units of half plus integer. So it's like the top stays at half, and the bottom goes like minus half, plus 3 halves, plus 5 halves, and so on. And then you see the sum, essentially, which in this case was 0 and 1, and so on. Yeah, that would be nice. I would probably have to. So this was 2 weeks back. So I am. They do degrade also, actually, so that's another concern. So we're actually trying to actively encapsulate them and so on. So this is this whole graphene and BN business now applied to topological insulators, where yeah, well, I'll have to write proposals to get time. Yeah, okay. So you've done that?
I'm on the external advisory.
Oh, okay, then I will be writing them for sure. Yeah. Yeah, but yeah, so so I guess I would basically then make a 2-pronged approach, where we are trying to improve the quality of the samples, but also try and take them over. Okay, yeah, that's good to know. Yeah, Yangshi.
Somewhere you mentioned the flat band insulate. That's related to the nanoorganic?
So Feng has, let's see. Right, so Feng has predictions where, using such metal organic frameworks, essentially metals linked by organic ligands, he finds that if you have a hexagonal lattice, you essentially have a Dirac system. If you have a Kagome lattice, you actually have these flat band materials. So that's the kind of work that we are trying to realize. So.
Normally, people want to have the so-called hot interactions and so on in the flat band. However, the interactions in the nanoorganic framework actually may be different from the
Okay. Right. Yeah, I'm guessing that Feng has some idea on what those interactions are. So I mean, you're assuming you're talking about on-site interactions.
Right.
Yeah. So, and they need to be high, or do they need to be low? They need to be high, right? Right. So I think one of the strong points of organics is that there is strong charge localization. So it's possible that those interactions are high. But again, from a computational point of view, that is, that's something that Feng probably has thought about. So I would say, in terms of an experiment, we are not really at the level where we are even able to make those churn insulator, not the churn, sorry, the flat band insulator materials right now. Mostly we've been focusing on, on the topological insulators, basically the quantum spin Hall ones, and just your regular metal, like the one I showed, which actually we hope will become superconducting at low temperatures. But the next steps would be to look at those more exotic ones. So, yeah.
Topological insulators that we were doing the quantum Hall measurements on,
Mm-hmm.
how big was the bulk, I guess? Like how far separated were the two surfaces?
Okay. So in this case, they were 90 nanometers apart. Yeah. So so we've actually seen different results in materials based on how thick or thin they are. In materials that tend to be fairly thin, we actually seem to be presumably gating both the top and the bottom surfaces, and that's ending up messing up our observations. And so it's nice to begin with to just have one surface stay at a certain charge density and just gate the other one. But I would think in the long run we would actually want to have two separate gates on both of those guys to change them individually, independently. Yeah.
So I guess how does that compare with how much an electron might be into the bulk?
Oh, it shouldn't leak. I mean, so I think theory tells us that at about 5 or 6 layers, each layer being a nanometer thin, you should essentially stop seeing any leakage. So 5 nanometers or smaller, you might have the two surfaces talk to each other. Any bigger than that, there should not be a problem. Christoph?
I have a technical question.
Okay, yeah, sure.
Of course, I'm most excited about your microwave setup.
Oh, yeah.
What kind of modes do you have there? How homogeneous are these fields? How strong are they?
Okay, so what we're trying to do here is actually, it's more of a guided microwave kind of a geometry. So okay, so what we're studying, or what I want to study, is the microwave transmission, right? So the S21, if you like. So what we're doing is, okay, so our microwaves come down. We have 4 different coaxes. So these coaxes then go onto our 4 ends of our sample holder. And then they are, so this is actually a way to, this is kind of, I want to say, an improvement on the sample holder design that I had when I was a postdoc and doing something similar. So essentially, we're trying to we're trying to cut down on parasitics of all sorts. So when you're looking at microwave transmission, your S21 spectrum essentially depends a lot on your parasitics, your parasitic capacitances. So just having really good shielding essentially is mostly what we're looking at right now. So so a microwave tight box with really good shielding, and then all of these microwaves come down here to these 4 different corners of this little thing. And then what we're going to be doing is we want to put our sample in here, and then the sample itself will have some sort of GSG kind of lithography done on it to guide your microwaves down to the sample. So yeah, so a bunch of this work is actually being, well, so so we are actually making our sample holders and the samples and so on. For the design of the devices themselves, I'm hoping to talk to my collaborator Berardi Sansale Rodriguez, who is an electrical engineer, and hopefully he will be able to assist us more in that.
You don't simulate these structures?
Not yet. We haven't done that yet. We'll be doing that together with Berardi, I think. Once we start making the samples. Yeah. Yeah.
In your metal organic framework,
Right. It turns out, oh yeah, okay. Right. Yeah, so it turns out that these are the ones that have the best coordination with the organics. So we actually had started out. So our computational collaborator Feng actually had the idea of using really large, really heavy metals, really heavy elements like bismuth, which have really large spin orbit coupling, and he had calculated that at room temperature, easily this should be a quantum spin Hall, state or topological insulator. It had a gap of, I want to say, a couple hundred or 300 MeV or something, except that, bismuth doesn't actually want to bond to these organic ligands very much. So then you talk to the chemist, and she tells us that these are probably our best shots to begin with, just because they just know their chemistry so well, right? And so you mix these guys up with the corresponding ligands and so on, and you actually get some really nice looking sheets. And so it does look like like the ligands really like these metals. For us, it turns out that these metals are definitely heavier than carbon, so definitely a lot more spin orbit coupling than what one would have gotten in graphene alone. So that raises your gap, your energy gap, or basically I guess I could call it an energy gap. The characteristic temperature at which you would want to see this from microkelvin to about 100 Kelvin, right? Not quite room temperature as one would get with bismuth, but something that can be that's doable. Yeah. Mm-hmm.
Wait, so like there's always a correlation between like more heavier atoms, higher spin orbit coupling, and like a larger band gap?
So heavier metals and larger spin orbit coupling, yes. Band gap, I'm actually not talking about band gap. I'm talking about the energy scale over which, I guess the stability in some sense of my topological ground state, okay? And that it just scales with the spin orbit coupling.
Stability of topological graphene.
So I have a Dirac cone, which is my my quantum spin Hall state, right? That Dirac cone has a certain window over which it is good in energy, right? And that window is the scale that I'm referring to of energy. So yeah, I'd probably have to, let's see. We can certainly talk about this in more detail, but yeah, this one's, for example, it would be this band crossing, which is linear, and it looks like it has a reasonably large window in the y-axis, which would be my energy scale, right? And so it's telling me that, okay, over a certain amount of energy, this state is going to be a Dirac state, right? In graphene, for example, that window is like EVs, like a few EV, which would mean that graphene would be a Dirac material up to, like many thousands of Kelvin.
I think
yeah.
we've kept you enough with questions here, so let's thank
Thank you. Thanks, Doug.